In Sussex, Harry's team produced more theoretical models. He worked out possible structures of other carbon clusters that had appeared in the laser. A hypothetical family of fullerenes was born.
One thing that was clear was that all the pentagons were isolated and all the hexagons were linked. That seemed to be a critical factor in the stability. And I started to think at what stage that would occur again. I knew it couldn't happen for anything less than 60 atoms. And as I went on higher and higher, I realized that I couldn't do it again until we got to the number 70. We'd already got a structure for 70 in which we take the two halves apart and we put an extra 10 carbon atoms along the waist. And then I realized that this explained the second peak. Now, we had found that the C60 signal always had a companion, C70, and I used to call the two together the Lone Ranger and Tonto. At that point, when you have a hypothesis which explains two major results, then you can be sure it's right. And at that point, I realized that I would not have to commit suicide over the Buckminsterfullerene idea.
But these models were still only theory. And further trouble lay ahead as Kroto and Smalley strayed into an area of science where they were outsiders.
It was natural to wonder about how such a beautiful molecule actually could form. And we thought that perhaps it started off as this sort of saucer-shaped structure, which actually accumulated more and more carbon atoms and grew into these sort of bowl-shaped structures and further more into larger ones which actually overlapped. Some of them would actually accidentally close and form C60, but most of them we expected would overshoot and then spiral to form large structures like this, ultimately ending up like this as large carbon microparticles. And then we realized that probably we had a nice explanation of the way soot particles form. Now, we proposed this, and it turned out to be rather contentious.
Those who study combustion, so-called soot chemists, were skeptical. The mystery of how soot forms when carbon fuels burn has perplexed scientists for over a century. Its solution could have enormous consequences for industries that use fossil fuels. Kroto and Smalley's model was new and surprising.
The technological implications of that model, particularly the aspect of it which said that if you could terminate the growth of soot at C60, so that by successfully closing the shell, you would not grow larger molecules, has a technological implication that if you could actually cause that to occur in systems that generate soot, you would generate particles of such small size that they would probably not represent a significant health hazard.
But critics scoffed at the idea that buckyball chemistry helped create soot. In none of the flames that soot chemists study had buckyballs ever been found. Many scientists skeptical that C60 even existed viewed Smalley and Kroto's soot proposal as more hot air. To counter their critics, they would need to capture C60 in a lasting form. Harry, backed by the British government, bought a laser beam of his own. If they could hold C60 in their hands, they could explore its true properties, how it might be tied to soot, and other intriguing puzzles. Harry's thoughts were on stardust.
Apart from proving it, there was another major impetus, and that was the fact that I still felt that C60 had some tie-up with the diffuse interstellar bands. And if that could be proven, that would solve one of the longest-lasting problems in astronomy.
Could buckyballs be behind the mysterious absorption bands? Were they in the stardust? The stability of C60 in intense laser light meant it might well survive if formed in space.
Turns out that C60 is extraordinarily photoresistant. It is the most photoresistant molecule of anything we've seen, which will be very important if C60 is to be found in space, because in space, molecules don't have sunglasses. You've got all these stars out there. What's to protect this molecule from getting sunburned over the hundreds of millions of years as we're wandering out in space?
But to find the absorption spectrum for C60, they had to make enough of it to analyze. They hoped that somewhere in the lasers, C60 had remained intact, but it was never to be found in the laser soot.
So for years, actually, squandering the life of my major graduate student, Jim Heath, we scraped soots up, put them in test tubes, sloshed them around and looked, and for years all we saw was soot sort of floating around or sitting at the bottom. Well, it's a lot of fun to do for a while, but for a year and a half it gets to be kind of boring. So we pretty well gave up.
The experiment at Rice came to an uncertain end. But even without an actual sample of C60, theoreticians kept churning out paper after paper, predicting the properties of such a molecule. The perfect symmetry of C60 allowed scientists to calculate how a buckyball would rotate and vibrate. They also could calculate how the molecule and its electrons would move when struck by light. C60's absorption spectrum, at least in theory, was available in print. When Don Huffman read these predictions, they brought to mind his long-past experiment with carbon dust and the surprising double-humped band he had produced.
When I saw the Kroto-Smalley paper in Nature, I was very excited because I immediately began to think that perhaps the camel sample wasn't junk after all. One of the calculations had to do with the ultraviolet spectrum to be expected of C60 molecule, which had a series of very strong bands in the ultraviolet, looking something like that, if I remember it. And if one put that on the same scale as our camel spectrum, there was a nice, interesting correspondence there. And this kept us wondering for a long time. Unfortunately, that was about the time when I was very busy with other things, and I went to the laboratory and had trouble reproducing the camel spectrum.
So he sent a graduate student to make carbon dust that would reproduce the camel.
Well, this was my first job in the lab, so since not very many people expected it would work out, there wasn't really very much pressure on me to produce results. It's really a very simple experiment, which is a good thing because it was such a long shot. It's a simple device. There's a carbon arc discharge in a vacuum chamber with a little helium in there. There aren't very many things you can change. We changed the tip size, we changed the voltage and the current, but it turned out that the most important thing was the pressure setting. When you have the pressure at about 100 torr, which is about 1/7 of an atmosphere, those two funny bumps, the camel spectrum comes back, the thing that we had seen in Heidelberg.
They sent the samples to Heidelberg, where Huffman's partner, Kretschmer, put them into an infrared spectrometer. He saw 4 absorption bands, which, like the camel, were predicted for C60.
The main result was that those samples, which also showed this peculiar UV feature, which we called camel hump, these samples also show 4 infrared bands at almost exactly the same positions as predicted by theory for C60. And we did publish this, and we could show that the 4 infrared features, at least, they are definitely produced by carbon alone, and they are not any kind of junk.
At the same time, we were very alarmed because in publishing the letter on the dust, we had essentially given away the secret, and if we could figure out how to extract C60 from the soot, then any real chemist certainly could, and they probably were falling right behind us.
So the secret was out. Kretschmer presented their results at an astronomy conference in Capri, and the paper found its way to Harry Kroto.
Well, I received this paper, which Mike Dura sent to me, and he wrote on the top, Harry, presented at Capri. Do you believe this? Question mark. When I read it, it was such a simple way of making C60. I just couldn't believe it.
Kretschmer's paper showed how to make carbon dust containing C60. Kroto wanted to go a step further, to extract C60 from the soot. He set 2 graduate students to the task. The race was on.
This is pretty ropey old stuff. When me and Amit first worked on it, it worked for about 3 or 4 days, and then all the electronics just burnt out, so I had to rebuild all the equipment. One of the things that we could do was the mass spec, and downstairs this was run by Ali Abdul Sada. And in fact, this is what happened. The sample was run while I was away in Scotland on holiday. And we got this fantastic result. Ali came down, clutching this bit of paper, saying, we have fantastic news. Do you want the good or the bad news? And the good news was that they got this peak where we expected for C60. And the bad news was that the machine broke down, so we couldn't repeat it.
They'd made C60, but how to separate it from the soot?
We'd been collecting it for several months. And so one Friday, one brave Friday, I had, I suppose, perhaps half this full of soot, and I thought I'd better do something. And one idea was just simply using a solvent to try and dissolve C60 out. So I got half of the soot I produced, and I basically just got some benzene, put it in the tube, and shook it up with the soot. Just shook it up, put it on the top of the shelf, and left it there over the weekend. When I came in on Monday morning, there was this red solution. I went round the laboratory going, look, C60's in here. And everyone was sort of going, yeah, okay, John. But it worked out in the end that, in fact, that's exactly what it was.
For 5 days, Harry thought they had the first solution of C60. But then?
Well, I had a call from Nature, the journal, and they said, would I referee this paper? So I said, fair enough, I knew a fair amount about this topic. And they faxed me a copy of their paper. And it was a bombshell. There they had beautiful crystals. They had infrared. They had an X-ray structure. They had made the molecule beyond all doubt, and we had been pipped to the post.
It was, of course, Huffman and Kretschmer's paper.
The amazing thing is that the whole process was so incredibly simple. Once we found that the carbon-60 was soluble as a red liquid, all we had to do is dry it out, and that left us with the solid that we were so eagerly seeking. The easy way to do that is just to pour it on a hot plate and let it dry for a few minutes, and there's the solid that we wanted to do the experiments with. Now, the way it really happened was Kretschmer called me from Germany and said, if you just take a little vial of the red material and you put a drop of it on a microscope slide, then you will see an incredibly beautiful sight. So I reproduced the experiment by putting a tiny drop of the red liquid on a microscope slide. And in just a very few seconds, as a matter of fact, I was able to see these beautiful little crystals, which were hexagonal platelets of brownish orange color.
No longer fleeting traces in a laser. What Huffman saw was a new solid, pure carbon crystals.
We realized by this time that we were surely seeing a crystalline form of carbon-60, which was really a genuinely new form of carbon, and that we were probably the first people on Earth ever to even see this sight.
This is the first ever film of a new carbon, buckyballs crystallizing before your eyes.
And as a solid-state physicist, it was incredibly nice to be able to say, aha, now we've got something that we can really begin to experiment with. We can see it and work with it. And that was really the moment of high excitement for me.
And here, suddenly, from a stunningly simple technique, by physicists, my God, not chemists, was the first macroscopic isolated amounts of carbon. Of course, we'd been scooped, but it was so wonderful.